Hello everyone, and welcome to a very exciting video, which is the first video on the Save My STEM Physics channel, which is not going to be about the boring basics of A-level physics. Today we are moving on to arguably one of the most exciting parts of A-level physics, which is a pun you will get hopefully at the end of this episode, and we will be moving on to quantum physics. Now, quantum has become quite a buzzword in recent media, but it is actually a part of physics. It is a part of physics that makes sense, contrary to popular belief, and it's one that is absolutely very interesting. Now, this also includes particle physics, and the way this is going to be run on this YouTube channel is we're going to do all of quantum physics, all of particle physics, and then all of wave physics, which includes refraction, total internal reflection, uh, and diffraction with like other stuff sprinkled in there, but generally that's what it's going to be. Now onto the quantum physics. That's obviously not what I've just spoken about. Yeah, so moving on to quantum physics today, we're going to go over some very interesting stuff, such as the electronvolt. These are all terms that we are going to define. The electronvolt, we're going to go over what is a photon. We're going to go over photoelectrons, and then we're going to culminate this all together for the photoelectric effect. Now, so the electron volt is a term which needs to be defined. This is a definition that you need to know, and this is a definition that I've got in my book here. Do I? Yes, the definition of an electron volt taken from the specification: work done accelerating. Sorry, I'm not going to be able to fit that. Accelerating. Just use a little dash. An electron, singular electron, through a potential difference of 1 volt. Now, work done is, obviously power. Well, not power, but work done. Energy transferred is in joules. However, the electron volt itself is an accepted unit, not the SI unit, but there is a conversion between the two, which you need to learn. And electron volts are used when talking about mass energy. So I assume many of you will be familiar with Einstein's equation of E equals mc squared, which is used to define the mass energy of a particle. That is quite frequently measured in mega electron volts, or electron volts times 10 to the 6. So, the symbol for electron volts, if we just skip down here, ignore these 3 lines, the symbol for an electron volt is very simply EV. And 1 EV is equal to 1.6 times 10 to the minus 19 joules. So that is the amount of joules required to accelerate an electron through a potential difference of 1 volt. We will go over what potential difference actually is when we move on to the electricity topic in whenever I get around to it. So yes, that's what an electron volt is. Similarly, if we have 1 joule, that is going to be equivalent to 1 over 1.6 times 10 to the minus 19 EV, which is equal to 6.25 times 10 to the 18 electron volts, if I'm not mistaken. I may have got the power of 10 wrong. If one of you could, well, if you could punch that into the calculator yourselves, just to confirm that that is correct, and then you can successfully keep that in your mind for your physics exams. Now that we've gone over what an electron volt is, we can use it as a unit for a very small amount of energy transfer. We'll go over our next question. What is a photon? This is a definition that you also need to know. Photon is, quite simply, a packet of energy. So it doesn't get any more complicated than that. When defining a photon, you don't need to discuss things such as a particle of light or any such thing. You don't need to discuss any sort of wave-particle duality which may come with that, which is a lesson we will get to in the future, in the near future. But simply, that is a photon. That is a definition that you need to know. Finally, what is a photoelectron? A photoelectron is an electron emitted from a metal after absorbing a photon. Now, this is due to the photoelectric effect, which is something we are about to get onto, but effectively, when an incident radiation or incident ray or incident light, typically ultraviolet light of a high enough wavelength, is incident on the surface of a metal, electrons become excited, which is what the pun earlier alluded to. Excited means gaining energy and going up energy levels, and they may gain enough energy in electron volts to escape the surface of the metal, to be emitted or liberated from the surface of the metal as a photoelectron. Now we'll go over the photoelectric effect in more detail now. So we have a metal here, right? Kind of a shoddy drawing of a metal, so I'll give it just a little bit more dimension. We have just a bar, a lump of metal here. Imagine that it's a wire, and we know from GCSE chemistry that a metal is made up of cations in a sea of electrons, right? Those little dashes are electrons, they're negatives. And what we have is we have incident light. Imagine that's a better ray. We have incident rays of light, ultraviolet light specifically for the photoelectric effect. And one important thing to note is ultraviolet light is an electromagnetic wave which follows the equation C equals F lambda, or C being the speed of light, so 3 times 10 to the 8 equals F lambda. And because the wavelength of ultraviolet is less than that of visible light, it must have a larger frequency, as this term stays the same. The 3 times 10 to the 8 is constant for all waves on the electromagnetic spectrum. So, what does this mean and why is it important? So, when any electromagnetic wave is incident on the surface of a metal, it causes electrons to be excited. However, there's this idea of the electron well, which some of you may have seen before, some of you may not. Absolutely okay, and it is not necessary to know for your A-levels, but it's a good bit of understanding to have. All electrons lie at the bottom of this electron well. However, when they are excited, they go up to these different rankings, which are the energy levels, and once they go high enough, they get emitted from the electron well, as we say, and that means they have been liberated from the surface of the metal. However, it can't take 2 pulses of energy, so those 2 arrows there are rather sort of incorrect in a way. It should just be 1 singular arrow. It has to be the entire energy takes it all the way up. Because what will happen is if it only takes up to that first rung, that first rank, it will immediately relax down to the ground state, that bottom area of the well. So, how does this link to how the frequency matters? Well, the frequency of the sorry, that's kind of not amazing. The frequency of the electromagnetic wave is directly proportional to the energy transfer to the electron, which means that it can escape, it can be liberated from the surface of the metal. Now, I've already discussed ultraviolet has a shorter wavelength than visible light, so its frequency is large enough, and we label this frequency the threshold frequency. Now we will get onto how to calculate threshold frequency at another point in time. But each metal has its own distinct threshold frequency. Threshold frequency is not constant for all metals, not constant for all materials, but it is an important thing to know about when discussing the photoelectric effect, especially during exam questions where it may ask during a multiple choice, the frequency here is less, the frequency here is more, and uh, during the one where there's a larger frequency, electrons are emitted. During the one with less frequency, with lower frequency, sorry, electrons are not emitted, and you have to explain why. The explanation is simply the one with higher frequency has a frequency above the threshold frequency. Frequency doesn't sound like a word anymore. I apologize for that. Has a frequency above the threshold frequency, meaning electrons can uh, gain enough energy to be liberated from the surface of the metal. So those are our ideas of threshold frequency, and the actual definition of threshold frequency is the frequency, sorry for the bad handwriting, it's because of that bit there, and also I just generally have bad handwriting, of an EM wave, sorry, required to liberate an electron from the surface of a metal, but frankly, I can't be bothered writing that again. And the kinetic energy that an electron, a photoelectron, is emitted with is proportional to the intensity of the wave. So, so an intensity can be as high as physically possible, but if the frequency of the wave is not large enough, then no electrons will be emitted. However, if the frequency is above the threshold frequency or even equal to the threshold frequency, as long as the intensity is large enough, uh, or larger, the kinetic energy of the electrons increases. And this is calculated using kinetic energy maximum, EK max, EK being kinetic energy, equals HF minus phi. We will get onto what phi is in a later lesson, I believe. Let me just check my book. Doesn't seem so, so I'll go over it now. Phi is the work function of the metal. That's kind of a bad drawing of the letter phi. It's more like that. You may have seen it before. And work function is just the amount of energy needed to wait, let me actually have a look at what the definition of work function is here. The minimum amount of energy in joules or electron volts, doesn't matter which one, as long as you can successfully convert between the two, required to liberate an electron from the surface of a metal. So very similar to our idea of threshold frequency here. And also we need to have a look at what H equals. This is a very important term in particle physics, and it is Planck constant, or the Planck constant, Planck's constant, the Planck's constant. All of them are accepted terms. They all work. Planck can be spelt basically however way you want. It could be PLNCK, PLNK. They're all acceptable. And it is roughly equal to a value which I have forgotten. It is in your equation booklets. I believe it's 6.63 times 10 to the minus 34. I'm not going to write that down in case it is wrong. But it is in your formula booklets for AQA level physics, and it's a number that I should know by now, but I don't. And basically the idea is, as long as frequency is large enough, EK max is greater than 0, and therefore we have overcome the work function of the metal. There is some more equations which you may need, such as energy of a photon, E equals HF. So you can sub that back in. The energy of the photon minus the work function is equal to the maximum kinetic energy of the photon. We also know from this equation up here that C equals F lambda, so you can write E equals H, uh, wait, sorry. If we rearrange this equation up here, C equals F lambda, to get C over lambda equals F, you can sub that into our E equals HF and get E equals HC over lambda. I'm uncertain as to whether this is an equation that you get in your formula booklet, but you do get all the other ones required to construct it, so you should be able to derive it, or at least use it in some way during your exam. And those are all the equations that we will be going over for today. Those are our ideas of threshold frequency, work function, and our definitions of a photon, an electron volt, converting between electron volts and joules, and the first lesson on quantum physics. Thank you so much for watching.